Where do we come from? Our origin story shapes our identity and gives us direction. Our family story, our nation story, our race story, our religion story. So often these stories promote an us versus them view of the world. While this is good at creating a strong sense of group solidarity, it no longer works for a world in which we are all connected and need to get along. It's time for the story of everyone. When we tell an origin story, we tell a history. How far back we go changes who is included in the story. A very short story will tell of my family. A longer story will tell of our nation. A still longer story will tell of our religion or race. An even longer story will tell of life. When we choose to identify with the story of life, the story of everyone, we lose the us versus them part of the story. The biggest problem with stories that have attempted to unite us in the past is that they are ultimately not objective. So they were only able to unite people who chose or were taught to believe the same story, leaving the rest of us out. We need common ground, an objective story that helps us to understand the nature of reality and some shared values. That objective story is the story of life. Let's look at the story of life now. In the last episode, we looked at the basic building blocks of reality, particles and forces, atoms and molecules that make up everything we experience. But how did that happen? How did we get from particles to you and me? To tell this story, we need to go back to the beginning, all the way back to the Big Bang. Now, there are only a few minutes to tell this story, so this will have to be the Cliff Notes version. Perhaps one of the most amazing discoveries of Einstein was the simple equation E equals mc squared. Energy is equal to mass times the speed of light squared. What this means is that energy and mass are equivalent. Mass is a tremendous amount of energy at rest. This is why splitting atoms releases so much energy that we can utilize it for generating electricity or bombs. Basically, everything is energy at different levels of rest. We see this most clearly at the earliest moments of the universe. Our best tools of science allow us to go back to an infinitesimally small fragment of a second after the Big Bang. Before that is only speculation. Approximately 13.82 billion years ago, the entire universe was no bigger than an atom, an unbelievably hot and dense plasma of energy that began to expand very rapidly. The expansion caused cooling of the plasma, which allowed for energy to form particles and go back and forth. Remember, energy and matter are equivalent. E equals mc squared. As the universe continued to expand and cool for some time, energy was able to remain as particles. There is also a force that controls the behavior of energy and particles. We believe it was initially one force that differentiated as the universe expanded and cooled into the four known forces: the strong and weak nuclear forces, electromagnetism, and gravity. See our previous episode for more on how the forces work with particles. Around 380,000 years after the Big Bang, the universe had cooled enough for particles and forces to form the first and simplest atoms. Because the universe was continuing to cool, the opportunity to form more complex atoms had passed too quickly. Before the first atoms had formed, electrons were freely zipping around, but at a certain point, electromagnetism was able to capture electrons in orbitals around nucleuses, and this happened all at once, as all the atoms in the universe snapped together. When this happened, photons were released in a giant flash of light. The remnants of this flash are still able to be detected and is known as the cosmic microwave background radiation. In fact, if you're old enough to remember TVs that used antennas, the static you would pick up between channels was partly picking up that ancient flash. At this moment, or at this point in the story, the universe is a vast expanse of mostly hydrogen, the simplest atom. But the atoms were not completely distributed as they were expanding. Because some atoms were closer to each other, gravity got to work in the next phase of the development of the universe. In the previous episode, I talked about the basic building blocks of particles and forces that make up atoms. One of the forces we talked about was gravity. Gravity is a force of attraction for everything that has mass. So even though these hydrogen atoms are very small, their mass causes those that were closer to each other to start to get even closer, which in turn increased the gravitational pull, collecting even more atoms. Eventually, the universe was filled by giant hydrogen gas clouds separated by vast regions of empty space. And these giant gas clouds were the beginning of galaxies. Within these vast clouds, atoms are drawn still closer to each other, and as they do so, gravity gets stronger and stronger until they become so dense and hot that fusion starts to happen. It's the release of energy as the atoms are smashed together at unbelievable pressure. The energy pushed out back against the gravitational condensing of the cloud of atoms, and the process stabilized into a star. At this stage of the universe, then, approximately 200 million years after the Big Bang, we have galaxies of bright stars. Within the heat and pressure of the stars, simple atoms of hydrogen with one proton and one electron combine to form larger atoms with more than one proton and electron, like helium. We call these different types of atoms elements. Eventually, stars burn up and use up all their fuel, as a star will then either collapse into a black hole, or if it is a big enough star, it will explode, releasing all of the known elements back into space. And new stars will form out of the debris. With these new elements, planets are now able to form. Our sun formed about 4.5 billion years ago, in the way that stars normally do. There was enough of the other elements in the orbit around the sun to form the planets of our solar system. Planets form in essentially the same way as stars, in that you have the atoms drawn together via gravity, and the difference is that because you have different atoms of different sizes, that is, different elements, and because the total mass is far less than a star, it forms a different type of structure. As gravity works on the elements that make up the Earth, it grew and became more dense, creating sufficient heat that the elements melted. In this molten state, heavier elements like iron made their way to the center. Different layers of matter were created for our Earth's crust. About 3.8 billion years ago, the Earth had cooled enough to allow the outer rocky crust to form. This is called the lithosphere, the rock layer of our environment. Then the continued outgassing from the molten inner core and condensation formed both the hydrosphere, that is the water layer of our environment, and the atmosphere, the air layer of our environment. Our Earth is not a solid rock. It is chemically active, and there is continuous movement from the inner layers out and the outer layers back down again. The continents are floating on molten layer and move ever so slowly, about the speed that your fingernails grow. This dynamic planet, called Earth, with an abundance of water and atmosphere to help protect the surface from too much radiation from the sun, created the right environment for life to emerge, the biosphere. I will address this amazing development in the next episode. Now I want to pause for a moment and reflect on what we have seen so far. A key feature we are witnessing is the emergence of complexity completely within the basic building blocks of reality. A few particles like electrons, protons, and quarks, bound by a few forces like the strong nuclear force and electromagnetism, form atoms and molecules, and gravity acting on mass combining to form everything we see and experience. The basic stages of the universe are the Big Bang of hot, dense plasma starts to expand rapidly. As the plasma expands, it starts to cool, allowing energy to form particles. Then particles form atoms. Next, atoms pulled together by gravity form stars. As stars burn out and die, larger elements are formed that are then collected again into stars, and the larger elements begin to form planets. each step forming a more and more complex structures, which make the way for yet still more complex structures and processes. This is evolution happening at a cosmic level. The theory of evolution, which began trying to understand the emergence of complexity within living organisms, is now understood to be at play in all other domains of science. Evolution is one of the most profound discoveries of science and has helped us to recognize that the universe is not a collection of discrete, separate systems, but is in fact one giant, all-encompassing system. Everything is truly connected. It is mind-boggling to consider the vastness of this system, everything that you and I are fully a part of. Now, this has only been the first half of the story. Join me in the next episode as we explore the emergence of life on Earth.